Hi everyone, so this is a discussion on chapter 1.1, which is graphs of equations, and I've written here that an equation in two variables has solutions that are ordered pairs. An ordered pair, you think of just a set of two numbers, x comma y, and we'll see that right now. What I'm going to use here is a table to find these solutions. So let me create a table, column for x, column for y, and you can make it as long as you want really. To fill this table out, you'll pick a value for x or a value for y and solve for the other variable. So for instance, if x is a 0, we can plug in 0 into this equation. We'll get 0 plus 3y, which is just 3y, equals 6. Divide by 3, we get y is 2. Similarly, if we were to let y be equal to 0, you can actually solve for x, and right away you'll get x is equal to 6. If x was 1, then what would you get? If x was 1, then you would get something kind of funny. Let me show you. So when x is 1, you get 1 plus 3y is equal to 6. Subtract 1 from both sides. 3y is equal to 5, divided by 3, and y is 5/3, which is not really a nice number, so it'll be hard to plot this when we plot these things, but we'll see that shortly. The last thing I want to do, though, is plug in y equals 1, and we can kind of see that when y is equal to 1, this equation will become what? It will become x plus 3 is equal to 6. So x would have to be 3 to make that work out. So we're going to take a look at these as ordered pairs and plot them in this next part over here. So here I've written that the graph of an equation is the plotting of its solutions. That's what a graph of an equation is. It's the plotting of the solutions of the equation. So let's graph the equation we just saw here. All we're going to do now is plot these ordered pairs on the xy plane. I'm going to try to be as to scale as possible, but it may not be completely perfect, but that's okay. We don't have any negative values, but I'll just include them anyways for completion, I guess. So the first point I have here is 0, 1, so x equals 0, y is equal to, I meant to say 0, 2, sorry. So 0, 2, and 6, 0 is where x is 6 and y is 0. Right there, and 1 comma 5/3. 5/3 is, well, if you write 5/3 as a mixed number, 3 goes into 5 once with 2 remaining, so it's 1 2/3. Meaning if you wanted to plot it, the y value would be 2/3 of the way between 1 and 2 on the y-axis. So since the x value is 1, we should have a point that's roughly about here. Something like that. The last point is 3, 1. X is equal to 3 and y is equal to 1. And what do you notice? If this is to scale, which is not quite, but what it should look like is that these points all lie on the same line. So imagine that's a perfect line. And that would be the graph of the equation here. Now, not every equation has a graph that is a line. Graphs that are lines have equations that are called linear. So this equation, for instance, is a linear equation mainly because its graph is the shape of a line. And we'll see a few more examples right now. Okay, so now for these next two examples, we're going to graph these equations. They're a little different though. So for this one, I'm going to subtract 2 over to the left to get y by itself. We go y is equal to x squared minus x minus 2, and now we'll create the xy table. So we're going to plug in different values of x and solve for y. When we do that, let's see what we get. So I'm going to plug in -2, -1, 0, 1, and 2. And the benefit of solving for y first, if you haven't realized already, is that there's no solving to do after you plug in. So once we plug these x values into this equation, it'll spit out what y is right away. So let's see. When x is equal to -2, we get -2 squared is 4, minus -2, which is plus 2, minus 2. The 2's cancel, we just get 4. So the y value is 4. For y. When x is equal to -1, what do we get? Your y is equal to -1 squared is positive 1, minus -1 is a double negative, so it's plus 1, minus 2. That's 2 minus 2, that's 0 for y. And the rest I'm going to do in my head, but say the work out loud. 0 squared minus 0 is 0, minus 2 is -2. 1 squared is 1, minus 1 cancels, and that's 0, minus 2 is -2. 2 squared is 4. Minus 2 is 2, and then that minus 2 is 0. And I'm going to notice something that I kind of should have said last time, but that's okay. I'm going to write it here. These three values that I'm arrowing are going to pop out to us when we graph them, when we plot them. So let's plot them and see what happens. What am I talking about? Well, first off, the highest the y value goes is 4. And the highest, I guess the lowest it goes is -2, so let's go down to -2. And then for the x values, I'm going to go from -3 to 3. I'm not labeling all of them, but that's okay. So now let's see if we can plot them. -2, 4 is over here. X equals -2 and y is equal to +4. Perfect. -1, 0 is right here. The x value is -1, but there's no y value, so it's just on the x-axis. 0, -2 is, well, the x value is 0, but the y value is -2. 1, -2 is right next to it here. And 2 zeros up here. And the shape we get, it's not obvious. If you connect them just as is, you won't get the shape I want to show. But actually, if you plot all of the solutions, which is really hard to do, but just kind of take my word for it, you'll get the following shape. Which is called a parabola. So I said before that all linear equations have graphs that are lines. All quadratic equations have graphs that are parabolas. Now the word quadratic basically means that it's a polynomial of highest degree 2. So the highest power is 2. The degree of the polynomial is 2. So if you have x squared involved and that's the highest power, then it's quadratic, so its graph is a parabola. So long as you're not dividing by x or don't have any radicals that include the variable or anything like that. But yeah. So something interesting happens with parabolas. The first interesting thing is that there is what is called symmetry. And let me include right here in dotted black. If you actually make a vertical line that passes through the x value 1/2, this is the vertical line x is equal to +1/2, by the way. There is a symmetry along this line, meaning that if you reflect the left side over to the right side, you get the same image, same mirror image. Which is kind of nice is we can actually see that in the table. So notice, this value is the same as that value, this y value is the same as this value, so this y value better be the same as this y value. Rightly so, because 3 would correspond to the same y value, 4, if there is indeed symmetry. So that means when you plug in 3, we better get 4, and let's see. 3 squared is 9, 9 minus 3 is 6, and 6 minus 2 is indeed 4. Perfect. And yeah, so there's one more thing I want to say about this particular example. And it's something we kind of could have spoke about in the previous example. And there are these points here. Now these points here are special in the sense that they lie on an axis. This point lies on an x-axis. This point also lies on an x-axis. These are called x-intercepts. This point, however, doesn't lie on the x-axis, but it lies on the y-axis. So it's a y-intercept. It's where the graph intersects the y and x-axis. So they're called intercepts. So now looking back at the table, is there any way we could have seen ahead of time that they are going to be x or y intercepts? Well, notice, if we just label them, -1, 0 was an x-intercept. 2, 0 was a y-intercept. Oh, was an x-intercept, excuse me, x-intercept. And 0, -2 is a y-intercept. So how can we try to recognize these? It's the opposite value is 0. See that? With the x-intercepts, the y value is 0. With the y-intercept, the x value is 0. So keep that in mind. That's basically how we'll be solving for x and y intercepts. You set the opposite variable equal to 0, and then solve for the remaining variable. That'll be that intercept. So if you solve for y, when setting x equal to 0, that'll be a y-intercept. Okay, and I'm actually going to do that here for this one, because it's a little harder to graph. Yeah, so let's do that. I said we can isolate x or y. I'm not going to, though, for this one. We'll kind of explain why in a little bit, but let's just first see if we can find the intercepts. So first off, if we set x equal to 0, that'll give us a y-intercept. It's kind of funny, though. Because what happens when you plug in x equals 0, you get 0 plus y squared is equal to 4. So y squared is equal to 4. And you may think, well, 2 squared is 4, so the answer is 2. Surely y is equal to 2. And that's not quite right. It's close, but it's not quite complete. And the reason is that though positive 2 squared is positive 4, negative 2 squared will also give you positive 4. So the answer here really is 0, 2, and 0, negative 2. There are two solutions that correspond to that we'll see more in a later chapter. Similarly, if we let y equal to 0, you get the same thing but with x's. So if you plug in y is equal to 0, you'll get x squared plus 0 is equal to 4. That means x squared is equal to 4. So then x is either plus or minus 2 because of that scoring a negative situation will give you the same answer. So we get positive 2 and negative 2 for the x values there. So now let's see if we can plot these points. So in this case, there are 2 x-intercepts and 2 y-intercepts. Try to draw this to scale. So for the y-intercepts, we're going to have 0, 2, 0, negative 2. For the x-intercepts, we're going to also have positive 2 and negative 2. And again, if you just connect the dots as is, you may not get the shape I'm about to get right now. And just kind of take my word for it again that we will get the following shape. It is a circle. So this, in this particular case, is a circle of radius 2. And if you're not familiar with what radius of a circle is just the distance from the center of the circle to an edge of the circle. So here the distance is 2. Okay. Speaking of circles, I'm going to show you a general case for the equation of a circle in a short second. But first I want to talk a little more about symmetry, and I'll do that right now. Okay, so here I'm going to talk a little bit about symmetry and just give 3 examples, and I think we should be okay. So there are 3 types of symmetry. There's symmetry about the x-axis, y-axis, and about the origin. And we'll discuss visually what that looks like, I guess, more geometrically when we graph it. But as far as looking at the equation and being able to tell if it satisfies any of these, it's just what I've been describing here. So about the x-axis, you would replace y with negative y, and if the equation looks the same, so there's no change in the equation, then it has symmetry about the x-axis. Here, if you replace x with negative x and have no change, that'll be symmetry about the y-axis. For symmetry about the origin, you would replace, I guess, both x and y with negative x and negative y, respectively, of course. And that'll give no change in the equation. So let's see what that looks like for these examples, each separately, of course. So here, if we replace x with negative x, you'll have negative x equals y squared. It doesn't look the same. But if you replace y with negative y, what you end up getting is negative y squared. Notice a negative number squared is still y squared in this case. So you end up getting this, which has no change. So what this tells us is that if we replace y with negative y, there's no change. So this actually has symmetry about the x-axis. Okay? I'm going to check the other ones, and then I'll graph them after the fact. And you'll kind of just take my word for the graphing, I hope. But let's see. Here, if we replace x with negative x, so here, a negative number to an even power will produce positive, so the negative goes away. But if it's an odd power, something interesting happens, the negative pops out. And the reason for this is that you can kind of see it if you do it out. Negative x to the third is negative x times negative x times negative x. There's a total of 3 negatives in multiplication, and negative times negative is positive, times a negative will be negative. So that's the reason why the answer overall will be negative. Because you have an odd amount of them, essentially. Okay? So the funny thing is, if you replace x with negative x, since the negative comes out, this will not be the same equation unless we also replace y with negative y. Because then just dividing through by negative 1 will give you 2x cubed is equal to y, which is the same equation. So this actually has origin symmetry. For this next one, this actually has all of them. Replacing x with negative x, and now replacing y, will give you the same equation. Similarly, replacing y with negative y will also give you the same equation, and replacing both of them will also give you the same equation. So I'm just going to check mark invisible spaces here, I guess. And we actually saw this one in the last example. But in any event, let me just show you what the graphs look like real quick. So I'm going to graph each of these in their own respective x, y plane, so we can see what I'm talking about when I say x and y or origin symmetry. So here the graph will look something like this. It's basically a sideways parabola that opens to the right. And notice this is definitely symmetric about the x-axis. At least I'm trying to make it look like it is. Here, 2x cubed is equal to y will look like this shape, which is symmetric about the origin, which I haven't described visually here, but what it really means is if you do a 180 rotation, you get the same image. Or another way to think of it is if you flip across the x-axis and then across the y-axis, you get the same image. But 180 rotation is the easier explanation, I think. And here we saw that this is a circle of radius 2, which actually does satisfy all three of those. It has x-axis symmetry, y-axis symmetry, and origin symmetry. Rotating to 180 degrees doesn't affect the image, it looks the same. Okay, so the last piece here to discuss for chapter 1.1 is the equation of a circle, and this is what is known as standard form. And the standard form equation of a circle is, well, it's just this x minus h squared, y minus k all squared equals r squared, where the point h comma k is the center of the circle, and r is the radius. And to kind of think back to that example we saw previously, I'm going to keep going back to that example. It was x squared plus y squared is equal to 4. Notice this actually satisfies x minus 0 squared plus y minus 0 squared is equal to 2 squared, which tells me that the center is 0, 0. So I'm going to write C, I'm going to label the center by capital C. So C in front of this point means that's the center. And the radius would just be what's squared on the other side, which is 2 in this case. So it's a circle with center 0, 0 and radius 2. Let's take a look at one more, maybe. So let's find the equation of the circle with center 3 comma negative 2 and radius 3. And then after we find the equation, we're actually going to graph the circle. So as it turns out to graph, we don't need to find the equation. We could just graph with this information, but I'm going to actually find the equation first. So first, let's label a few things, shall we? Let's label C as HK. This is R, so R is 3. And we get the following equation if we follow this standard form. We get x minus 3 squared plus y minus negative 2 squared is equal to 3 squared. Okay. I'm going to simplify just a little bit. X minus 3 squared plus y double negative is positive, so it's positive 2 squared is equal to 3 squared is 9. This right here is the equation in standard form. If you try to go a little further, there is something called general form, which I'm just going to show real quickly. And all we're going to do for general form is we're going to expand everything out and move everything on one side so the zeros on the other. And let's see that real quickly. So I'm going to expand out x minus 3 squared. So that's going to give us x squared minus 6x plus 9. Remember, it's the first one squared, 2 times the product for the middle term, and the last one squared for the last term. So let's see if we can do it for y plus 2 squared. It's going to be the first one squared. 2 times their product is 2y, so double that is going to be 4y. And the last one squared is 4. Combining like terms, and I guess subtracting 9 to the other side, will give us x squared plus y squared minus 6x plus 4y plus 4 is equal to 0. And this is called general form. I know I wrote the terms in a weird order. Basically, you write the squares first, the non-square second, and the constant last. And I didn't really show it, but if you subtract 9 to the other side, the 9's cancel. which is why we're only left with positive 4 here on the left, and 0 on the right, of course. And let me just write this is in general form. Okay, so in any event, we found the equation of the circle. And what we're going to do now is we're going to graph. And we don't even need the equation to graph. We can just graph with the information. So we have to be a little careful, though. Let's see if we can do it. I think we'll have enough space. Let's see. So first, let's go to the center. The center is 3, -2, which is over 3 spaces, and then down 2. And then we need to, so let me plot that. So that point right there will be our center. We're going to go up, down, left, and right by a distance of 3. So we'll need to go up 1 above the y-axis. We'll need to go 3 over to the right, over here. Let me plot these points. And this, of course, isn't to scale, but it doesn't look too bad, I guess. And then 3 over to the left, and then finally 3 down below. So 1, 2, 3 more, there we go. And if we connect all these with a circular shape, we should get the circle, which is the graph of the equation. That's good enough. Just imagine that's a perfect circle. It doesn't look too bad, I guess, but yeah, in any event. Yeah, so that was 1.1, and now we're going to see 1.2 in the next video. See you then.